Okay, here are our quiz 4 solutions for Math 243. So what's going? I'm curious if the amount of coffee I drink in a given day affects the number of times I laugh when watching The Daily Show. Okay, whatever. What's important is that what I'm saying here is that coffee causes laughing. In other words, when they ask me to determine the explanatory variable, which is the cause, and the response variable, which is the effect, when I read this sentence, I see that the cause would be cups of coffee. So explanatory is cups of coffee. Maybe cups of coffee that I drink per day. And the response is laughs. Maybe number of laughs. So these are my x's. These are my y's. All right, find the least squared regression equation and interpret the meaning of the coefficients. So what you gotta do is first put your data into lists. I did that already. My x's are in L1, my y's are in L2. And then you hit stat. And then you go to calc linear regression. And then I tell it where my x values are, which is L1. And then I'll put a comma in there and tell it where my y values are, which is L2. And then another comma. I could stop there, but I'm going to put another comma in and tell my calculator I want to save this under y equals so that I can later see the graph on the scatter plot. So the way you do that is you hit variables down here and go over to y variables and function and y1. So now not only am I doing a linear regression with these are my x's, these are my y's, but I'm saving this under y1. Hit enter. Gives you all sorts of stuff. Find the least squared equation, least squared regression equation. I get y hat equals 2.07. Let's call it 2.1 x plus 1.4. I still have to interpret those coefficients, but if I recall correctly, it's later going to ask me to figure out what r is. That's 0.756. Call it 0.76 maybe. And then later r squared, which is 0.57. So I'll copy those down for later and then go back to where I was. Interpret these coefficients. Okay, this 1.4 is kind of saying if x were 0, if I drank no coffee, I'd still laugh. I'd expect to still laugh 1.4 times. And then the 2.1 here, my slope, is saying that for every change in 1 in my explanatory variable, in other words, for every extra cup of coffee I drink, I expect to laugh this many more, so 2.1 more times. More because it's positive 2.1. Sketch a scatter plot. Include the least squared regression line on it. Okay, I can have my calculator kick one of those out. If you hit second and then y equals, you get under stat plots. Hit enter. Turn it on. Select the first type. My x variables are in L1. My y variables are in L2. And I've already saved my line under y equals. So if I just go to graph, if I look at this by hitting zoom and then zoom stat, which is number 9, it'll kick out both my scatter plot and my least squared regression line, which I can sketch down here. Let's see what x's were cups of coffee. And maybe y's were laughs. And get a scale here. X's go from 1 to 10. Y's go from 4 to 32. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then what did I say? 30 something? 5, 10, 15, 20, 25, 30. Do I need more than that? 32 looks like is the max. Let's go a little higher. Here is 10, 20, 30, something like that. And then I need to draw this line, and I need to plot all my points. Maybe I should switch colors. So let's draw the line. You can either do it by looking at the picture or by using your equation here. My y-intercept should be 1.4. So if this is 5, I don't know, here's 1.4-ish. And then for every 1 it goes over, it goes up 2.1. So every 10 it goes over, it goes up 21. In other words, it would go up to 22.5, something like this. So my other point should be roughly over there. And if I can draw a straight line, which I can't, but if I could, it looks something like that. There's my least squared regression line. And now I can kind of just put in all my data points. I mean, I could be lazy and be like, all right, there's one. The first one looks like it's right around on the line. Second one also right around on the line. Third one, pretty damn close, just below it. Fourth one, just above it. Fifth one, 1, 2, 3, 4, a little bit more above it. Sixth one, a little below it. Seventh, kind of similar. Eighth up here. Ninth way down here. And 10th way the hell up here. So good enough. There's my scatter plot, least squared regression line. Looks like that's good for 3. Determine R, interpret its meaning. Okay, it's positive, so we have positive correlation. 0.7, that's kind of on the borderline. I don't know, maybe moderately strong. Moderately, I think that's spelled right. Actually, I think that's spelled wrong. Moderately strong, positive. Actually, I have no idea how that's spelled. Moderately strong, positive correlation. One guideline is to use 0.7 as kind of your cutoff. Below 0.7 weak, above 0.7 strong. But I don't know, pretty close to 0.7. Maybe we'll call it moderately strong. Anything close to that's fine. But key that it's positive because it's a positive number. Yesterday was the last observation of the above data where I drank 10 cups of coffee and laughed 32 times. In other words, x was equal to 10, y was equal to 32. Calculate the residual of this observation. The residual is equal to y minus y hat, observed minus expected. So I know y is 32. I don't know what y hat is. I have to calculate that. I can do that off to the side here. Y hat I calculated earlier. The equation for my least squared regression line is 2.1x plus 1.4. But I know that x equals 10. So if x equals 10, I get 2.1 times 10 plus 1.4, which is 21 plus 1.4, or 22.4. So what I get here is that I actually laughed 32 times watching The Daily Show, but my line would have predicted that I laughed 22.4 times. So I laughed more than I expected. I laughed 9.6 more times than I expected. So my residual is 9.6. Maybe I throw a box around that because there's a lot of writing on this. And then what this means is I laughed 9.6 times more, because this is a positive number, than expected. All right, r squared, our coefficient of determination, we've already calculated that to be 0.57. Interpret its meaning. What that means is that 57% of the variance in y, so in this case the variance in laughs, the amount of laughs watching The Daily Show, 57% of that variance is due to how much coffee I drink. The idea there being that there's lots of different things that will affect how much I laugh. There's a lot of variance up here in number of laughs. One day there's only 4, one day there was 32. So a lot of different factors affect that. Who the guest is, what sketches they have, whatever. But according to this regression, 57% of the variance is due to our explanatory variable, how much coffee I drank. And then finally, number 7, sketch a residual plot for this data, and then explain what's going on. We can do that. You can get a residual plot straight out of stat plots. I think before I do that, I'm going to hit my y equals key so that I can turn off my linear regression equation, just so this line won't show up on my regression plot or my residual plot. And then go under stat plots, scatter plot. Just like last time, my x variables are in L1, but now instead of my y variables being in L2, I want my y to list the residuals. So I can get residuals here by going under list, second, and then stat, and then down to residuals. So my x's are L1, my y's are residuals, and now if I look at my scatter plot by hitting zoom stat, I get this. So I got my residuals over here and my x values over here, and what you'll notice is that it kind of has this pattern where things stay really close to the line. The residuals are close to 0 when we're on the left side, but then as we get out to the right side, they get kind of far from 0. So here's a residual plot. These are residuals. And here's my x values, which were cups of coffee. Which problem with regression is present? This is called heteroscedasticity. Heteroscedasticity. If you don't remember that word, that's fine. It's also known as non-constant variance. Sort of the idea here is that the variance in your y value should always be the same. But in this case, they're not. It seems like it varies more. They spread out more when your x values get large. So the problem is heteroscedasticity, aka non-constant variance. So we must take caution. When using our LSR, our least squared regression line, to predict large values of x. In other words, when x gets big, it starts to vary a lot on y. Our line's not as good as it used to be. So if you're going to make predictions using this line, be kind of careful if you're predicting large values of x. Know that your line might be wrong. There's a way to fix that, but there's not a way to fix that in this class. So that is the end of the quiz.